Okay, I'm Zeal Jagannath,
And I'm RonFenelus's.
and we did the shared shortest paths and graphs. What our problem basically was a generalization of the shortest path problem, where you have a graph such as this, and you want to route the shortest path for a particular journey through the graph. So in this example graph, this path outlined in green would be the shortest path. We generalize this problem by asking how to route more than one journey. So you would have a larger number, greater than one. In most cases, in the examples at least, we ran it on 3 or 4. In practice, you'd want it to run for an arbitrary number of journeys. But you want to route all of these journeys so that they have the minimum cost, or there were a variety of other ways we looked at the problem. Minimum cost was one of them. We used game theory to analyze this problem. First, we looked at the concept of a Nash equilibrium, where we try and find a configuration of journeys such that no individual journey can defect to find a better path. Finding these is usually very easy. We actually programmed an algorithm that finds them quite well in practice that we'll talk about later. Another variety of Nash equilibrium is a strong Nash equilibrium. These are much more difficult to find. They don't always exist, as we'll see in a minute, and when they do exist, they can be very, very difficult to find. In this example, this is an example of where a strong Nash equilibrium does not exist. In this example, we have the yellow and orange here will defect to go on this path and actually decrease their cost. So they will defect, and then after that happens, yellow and green will defect to the center path to split this and reducing both of their costs, and then finally green and orange will both defect back to their original path, forming a cycle. This shows that there's no strong Nash equilibrium for this graph.
And one problem with this problem is that it's NP-complete, and what that basically means is it grows very quickly as you add more input as your instance grows. So it takes a long time to find the optimal solution based on the total cost. So what we do is what we did this summer is we developed a heuristic, the spanning tree heuristic, that finds the minimum spanning tree, which is basically a tree, which is in a graph. A tree is a graph such that there's one path from any vertex to another. So in this graph, there's one path from any vertex to any other vertex. And we took the minimum spanning tree, which is basically a tree that links every vertex and is of minimum cost if you add the cost of the edges. And we route the journeys on this graph, and what that does is it encourages sharing, and it also, if the costs of the edges are, if they're in such a way that you can embed the graph into a plane, then this heuristic will only do twice as worse. 2 times the cost of this heuristic will only be twice the cost of the actual optimum solution, which is pretty good in that it doesn't grow with the number of journeys or input you add at all. It's a constant. You can relate it constantly to the optimum cost in general. Another thing we did was, as Zeal mentioned, we can find Nash equilibrium from any instance of the game that has paths already. What we do is we look at each path and we see if it can make a better choice, and if it does, we deviate that. We switch the choices until no one can make a better choice. The thing about this is we don't have an upper bound on the time this algorithm would take, depending on how many journeys or how big your graph is. So that's something we're thinking about doing. We're looking to kind of improve in the future to find a better way to analyze this algorithm. Another thing we wanted to look at in the future was what's known as the priceability, which, if you have a graph that's if you have a graph and a solution to it that's an optimum cost, how close can a Nash equilibrium get to that cost? So basically, what's the cheapest Nash equilibrium you can get based on total cost, and how does it relate to the general optimum solution that isn't necessarily Nash equilibrium? And those are things we're looking at in the future.